know if it's going to work. How do I? Okay.
Analysis webinar, December 4th, 2020. So here you see the software, you see the demonstration data set. STXM Ptychography is a specific folder for the data. These are huge. The total STXM Ptychography is 17 gigabyte. I don't recommend you download the demo data. It's just huge. So yeah, because you haven't studied many of you haven't studied with ptychography measurement. If you do ptychography measurement in the future, and the presentation could be a reference for you for data analysis. So that presentation file is over here, which you can download. I think Jay will be putting his presentation file on the same location later.
Yep, I will.
There are some reference. I think most of the references for Jay's presentation, like PCA analysis, ImageJ plugins, those stuff. There's the plugins.
Okay, so we take a 10-minute break till 10 after 11 Saskatchewan time.
Yeah. 10-minute break. Okay. Starting from 11 time. Yeah.
Yeah.
Okay.
Okay, I'm going to reclaim the host again.
Yeah, I stop sharing and
then I should have
slide.
just email Jan or Ying or me. We'll get them to you. I think we have to. Okay. We'll have to. I think we'll send something out to the user list, but just email Jan or Ying or me, and we'll get the information to you.
Thank you.
What you want to annotate my content? I'm not going to stop that. Okay, I guess we're probably ready to get started. Is Jan back?
yes, I'm back. Yeah, go ahead.
Yeah, I guess we'll get started, eh?
Yeah.
Okay, hello everyone. I'm going to present on PCA and cluster analysis, principal component analysis, cluster analysis. And just to let you know that the weather here is somewhere around 0. In the picture I'm showing, it's not like this out in Saskatchewan at this time. We've had around 2 feet of snow outside, 60 centimeters for those in metric. And we had one storm come through with over 40 centimeters of snow drop on us. So that's where most of our snow come out. But supposed to return to normal temperatures, or actually below normal temperatures next week. So be below minus 10 Celsius next week. So those are things that you're missing not being here. I'm going to go a little bit off script here. So I do have a PowerPoint here that I have a lot of slides for, but I'm going to show you the first 4 or 5 slides. Then I'm actually going to change it and go actually into the PCA program and do the analysis there. I think it's almost just as quick. Okay. So I'll just talk about principal component analysis and cluster analysis, and then I'm going to talk about why we want it and where you can go get it. So this is the references that you can go consult for the PCA analysis in Access. It's actually in Access. It's also a standalone program, like Janice said, from Stony Brook. We prefer to use a standalone program because it displays everything in color. Whereas Adams, he's incorporated into Access under the stacks statistics, but it doesn't show it in color. I don't know if it shows it in color in his licensed version, but in the virtual machine version, it doesn't show it in color. So we have a standalone, and if you don't have that, we can get that to you. Maybe we'll put that on our site too, so you can download it. But why do we want to do PCA analysis? Probably most of you know this already, but it helps us find things that we wouldn't know there. If we're doing just linear combination fitting, you can reference spectra. We may not find some unexpected compounds. So the goal is to identify any representative spectra and produce quantitative component maps. Principal component analysis, you can read about it and go and understand all the abstracts and where it all happens, how it goes. I'm not familiar with math, exactly how it's all happening. but it all arises from a singular a signature from a linear combination of several different chemical species, and so there's not a simple relationship between one abstract component and one particular chemical component. So it has to do with the matrix. We have eigenvalues, eigenspectra. And these are things that we're going to produce the program, and then once we get these eigenvalues and eigenspectra, they represent different spectra from our thing. From there, we're going to use those to do our cluster analysis. It'll group these eigenvectors together, and we'll get pixels that just represent the different spectra. So I just want to say before I go into the program, the PCA has evolved over time, and the angle was the method that was preferred. But we'll see that in the program, and what we're looking and versus Lucian. So we want to look at variations in thickness, and they're often classified as distinct regions. That's the problem with the angle, or is that variance in thickness are showing up, and we want to look at distinct regions with different spectra. We don't want to look at thickness when we're trying to figure out these which spectra are common and define them. And so the angle distance it measures rather than conventional Leucian distance measure, suppresses the thickness variations, and thereby cluster data based more completely on chemical speciation alone. So we want to use the ratio of the eigenvalues instead of the difference of the eigenvalues. And this is just some things that I've come to, some rules, is that the number of clusters to seek, you want to use more than you want. And so normally you try a high number. There's not going to be 20 different spectra that we're going to be able to differentiate in our thing, but it does help us find ones that aren't there. I find if you use too low a number, like 5, I'm going to show you that, we won't find some spectra. Also, significant number of components too. We want to try a higher number. So don't be afraid to try higher numbers and work your way back. So this is what I'm going to use as my criteria. I'm looking at aluminum spectra. This is my stack that we're going to look at. But if I manually extract, I can see a nice peak here. And I'm going to show you the results already of what I did with the PCA analysis. And this is what I mean colored. This here is an atom that comes out gray. And if you use the standalone PCA analysis, you get color, and these colors correspond to the difference in the same as the spectra. And so if you use too low a number of components and clusters, you will not identify this compound here, and I'll just show that. So the problem is if you don't see enough clusters, it may not identify all representative spectra. And so when I was looking at this originally, I manually extract things, and I go, oh, I found that. And then when I was playing around with the PCA, I couldn't reproduce this. I couldn't find this spectra until I started increasing the number of significant components and the number of clusters that I'm looking for. And so like I said, I do have all this principal component to do this, and exactly like Jan said, and I'm going to actually go do this now. I'm going to stop sharing this screen and go into this, and I do have all this how to look at this, but we're going to look at all this ourselves. I think it'd be better if we did it here. So I'm just going to stop sharing this, and then I'm going to share. Oh, where did it go? Here it is. So I'm going to share this. Okay, so this is the PCA GUI that's from Stony Bridge. This is the standalone. It's actually an Atoms thing, but again, I told you it doesn't do color. So the first thing to do is to load a file. So I've made a NCB file, and you have to, before you do anything, you can find the principal. You got to go in, like Jan said, you have to go and align your stack. And so we have this stack analyze, which is also an Atoms program, But Jan and I also we prefer to use the most recent version, and it's a standalone too. And we can give you that to show. Because the standalone is going to actually, right now, I can't read it in an I0 file till I load in the stack. But the I0 file requires an XAS format, and you can get that easily from the stack analyze when we analyze. You can get it to pick the I0 from the aligned stack. So I'm just going to go here and find my data. And recently, I had my computer was attacked by a virus last weekend, and so they've taken it away from me and took it away from me yesterday because they're still afraid that there might be some remnants of the virus. So we're of the virus. So I've had to things on here. So I'm just going to get the. I think this is it. The stack. It's already been aligned. Okay. Did I grab the wrong one? Okay. I thought it shows up here. Okay. Now this becomes active. I can go grab the XAS file. So it's just here. I think I opened the right one. Yeah. Okay. So now this pops up and says, "Are you happy with this?" This is actually I did two. I collected aluminum and phosphorus, but it'll just take the aluminum, I hope. So if you're happy with it, looks fine, you just say dismiss. And I get the feeling that I opened the wrong one. Because I should see here. Anyways, we can go into this pre-process. We can limit the energy range. So if I did have a stack for aluminum and phosphorus, I could tell I just want to look at the aluminum region. We can clip subregions, and we can also look at the optical density filter. And I explain all these in my PowerPoint further. I think I've let's see. So you just click on the PCA, and it'll tell you the number of components, and you can save this here. Okay, you can save it and open a lot of times in Access means here. So what do we get here? It tells us that there are 90 significant components. We know a lot of these components are noise. So I'm just going to reduce it down to something 20. And so this is one component, 2, 3, 4, and 5. Up to 20 I'm showing here. It's showing the spectra. And these are, the first one always looks like a spectrum. But the next ones, if you look here, this one looks like a spectrum. The other ones start to look like eigenvalues. Okay, and I can't explain what an eigenvalue is to you, but they're different ones, and you can see where they're occurring here. Okay, you can go up to probably 90 if you want. See. Okay, but I'm just telling it to look at the first significant values. You can save these eigenvalues, eigenspectra. You can save them as the images. These images if you want and stuff. I find that it's not too useful to move things, and I haven't really found useful to move components up or down, but you can move components up or down. So if you're happy with this part that you're here, this is very, very simple. You just say dismiss. And now it comes up here is now we can move into the clusters. So clusters comes up here. It still shows significant components. We can change this again. I'm going to leave it at 20. And now I'm going to tell it how many clusters to seek. I'm going to do 5 just initially. And actually, so I got this wrong. So Leucian is what we don't want. It's the angle that we want. But if I were to tell it to calculate now, it will calculate. It doesn't take, should come fairly quick. So it calculates here. And I guess what I forgot to mention on my PowerPoint is I really want, the first one is, the blue one is showing a lot of, it cut a lot of spectra off. And so if I move me out of the way here. So this is showing one spectra. We can go look at each one individually. And it found 3. I found 5. And if I look here, and if I look here, right now, I never found that one peak that I was showing you about, the spectra. It's there. I can manually find it, and it didn't find it here. Okay, so this is not one we want. So what we want to do is we want to use the angle measurement. So we just click on angle here. Now this becomes active. We can go in, and so what this is do we want to go in and cut off some of our noise. And the bigger you go, the more noise you'll cut off. But if you go too high, you'll start to cut into your actual image. And so I'm going to use a value of 0.1. I know that if I use 0.5, that I really start to cut the image off. And so you just say enter, and this shows where you're cutting off. But you can play around. This is something that I suggest that you play around with. And so you're just going, I'm just going to say, okay, I'm happy with it. Dismiss means I'm happy with it. Now I'm just going to tell it, and now we put in this eigenimage scaling factor. Before it was reading 0. You can change this 0.2, 0.4. I can't remember which way it goes which, but if you go one way, it reduces the number of clusters that you find. If you go the other way, it increases. It's a scaling factor. So here we're going to use 5 here again, and we're just going to calculate. Doesn't take very long. Okay, this time it found six spectra. And let's see if it found in this case. So it did find something similar to what I was able to pull out, starting to show it. But a lot of these spectra are, if you were going to look at them, most of these are even the same spectra. And this blue one now is always the first one represents the I0. There's always a little bit of the spectra in I0, but now this looks, if we were to go back to the original image, this looks proper. That's showing me the I0. If I were to have used the Elukian, this would be way bigger. And if you can remember, it was way bigger. This is one of the guides I use. That yes, I'm getting what I want, but even still, I'm not happy with what I got here. I could extract something better. So I'm just going to increase the number of scans here, or spectra clusters to seek. I'm just going to tell it to calculate again. Doesn't take too long. Okay, so now it found 11, it said. But this time when I do this, now I'm starting to get something more reasonable. It shows this what I had sorted before, but now it's showing this one here. And if I were to look at where it was occurring, it'll be, this is the one here where it's occurring. Whereas before I used 10, when I only used 5, it couldn't pick these out from the other ones. So the trick is you got to use higher than you think to try to find it. But a lot of these spectra, if I were to overlay them better, and here I can't overlay them, but take them into save them, I could overlay them, and you'd see that they're all you'd see that basically there's three or four spectra here. The purple one, these ones are all the same. This green one, and maybe this other one, maybe 4 different spectra here. So this is telling me that found 11. And these 5 or 6 of these are actually just based on differences in thickness. If we go back and look here, this is just difference in thickness in my sample. it's showing basically the same area, but just different pixels and just different thickness in the sample. Okay, so when you're happy or whenever you want to, and these here are matching the colors here, like I said. So in the Access version, these are gray, so it's not as nice to keep here. But now if you want, I'm not going to do it, but we can go save all these as different ROIs. Okay, we can go save all the spectra, and it'll save them as both CSV and XAS, and you can save our clusters as PNGs here. There's other things that you can go look at here. The dendrogram, I explain it a little bit more in my in the PowerPoint, but you can go look it up on the internet what a dendrogram is to try and get an idea of what different spectra are different here. It's taking a little time to load. So my suggestions are you can play with around significant components, the number of clusters. This you can play around, just determine, this will, can't remember which way, it'll just reduce or increase the number of clusters found and the cutoff here. Oh, maybe I shouldn't have done this dendrogram, it's taking a little time to load it. So I would play around with those and get it where you're satisfied what you're thinking. But I'm going to show you also the matrix, which is the next version of this, and uses this program here allows you to use zeros and negative values here. It's not showing it here, but the matrix one forces everyone to be above zero. And actually, I'm finding that I've just started using it, and I'm finding that it's actually better than this. And matrix it's easy to download. It's just a Python base here. This looks like it was a bad idea to do the dendrogram. It's taking a little while to load here, and I'm probably can't stop this. Someone wants to update me. Better remind me later. Okay. So if anyone had a question, so now you're seeing here that really a lot of these are just the same area. This is nicely coming out. There's different compounds here. And the blue is, again, the I0. And you could do this. Jan does it often, where he does it. I've done it just with the aluminum stack here. He'll do it with 6 or 7 stacks all together. And you can get relationships that way of different elements that are together. And so you just have to either have a stack that contains all of them together. You run it together, or you can join stacks together. And that's something that Jan explained briefly, but it's something that if you needed more information, we'd have to show you. So take it to this dendrogram. Oh, what's the other thing down here? Also down here, you can see that this is, I don't know if I can move this now. Nope, it crashes. So this is the number of pixels, and each one of these, again, colors refer to the spectra. So this is the percentage of pixels. They're all around 10%.
Hey, Jay, I don't know if it's on my end only, but all I'm seeing on your screen is kind of this gray mesh.
Yeah, I think because I tried to click on something here. I wonder if I can... yeah, but you could see the rest before, right?
Before, yeah.
Yeah, I clicked on it, and now it's showing... There we go. So there's the dendrogram. You can pick out the number that shows you which line represents which here, and relationships, which ones are related. Those can help you decide on which spectra are related. I'm not an expert on dendrograms, but it can help you decide. Here, I find myself, I just need to go overlay them, and I can get the same information as here. And so you can save this if you want, and go look at the different spectra, showing which ones are related and stuff. Okay? I think you should be able to see everything now. And the pixels down here again, showing everyone's around 10% of the pixels. Okay? And then if you're happy here, you've saved all these. You can save them. If you're happy, we can leave this now. And what else can you see here? Oh, here you can see here. This is the cluster number. The cluster one again. They correspond to the colors. And this one here. So you can get information here. You got a component weight here. You can look here. So component one is about 65%. So that's my I0. 16.9%. So you're seeing it's falling off. So 3.2, 4.5, and even 5 now we're starting to fall off. So the weight and cluster. So all this information can help you decide which ones are real. So if you're happy here and you've saved everything that you want it to take, because the ROI files you can read into Axis, the Axis files you can read into Axis. You can do things there. You can if you just want to overlay three of the images, you could do that in Axis, or take them. Also, you can take them in Axis, save them as a TIFF, and take them into image J. So if you're happy here, we're just going to dismiss here. And then if we want, I don't find the target spectrum mapping so useful. I find it actually to take the spectra and the maps better into Axis. But now I can add the target spectra. I'd saved them before, so it saves them as an XAS format or CSV. So spectra at 8, I think this is 8. I go here. Okay. There we go. So it loads it, shows which one I want. I can go load another one, number 5. Load any ones that you want. You see it. You can actually, this is the raw data. It can play around with fit it. It's given some residue here showing where it's occurring. You can go back to the first one here. You can bring in your own spectra. You move up target spectra and stuff. And significant components you can reduce here, and you can save these maps as PNGs and stuff here. So that's how to use PCA in Axis. Now if you click dismiss here, you go back, you can go another file, go back to your cluster analysis, and you can play around here. So I suggest that you play around here. I haven't found this to be useful, this target thing. I'm not sure that it was really ever completed, because to me, I really wanted to be able to overlap these spectra. This is showing where they are. I can see that because this is picking it out. If I go to the next one, it's showing where it is, and I guess it is showing here the red one is my previous spectra, but I don't find it's not as good as Axis that I don't find that you can overlay the images and get your color contrast and really see differences here. So this is all explained in my PowerPoint on how to click here and where to click and stuff. But it's relatively simple to use. You just have to understand what you want. It's going to tell you things. In this case, it's telling you more spectra than we think are there. Okay. Is there any questions? I'm gonna close this. Oh, can we still see my PowerPoint? Can you still see the PowerPoint? People?
No.
No. Okay. All right. Can you still see the PCA analysis?
Right now,
yeah.
All I'm seeing on my end is just a gray.
Okay. Okay. So I'm going to stop sharing this again. Were there any questions on that part? It's relatively simple to use. You just have to play around with the values and determine the values. But I'm going to actually show you the matrix, which I think is going to be better finding a spectra, and it's not showing so many duplicates that you have to go combine areas and stuff. Because so for there, even though I had I think 11 spectra, I could go combine 5 or 6 of those images together and combine the spectra, average the spectra together, and get the average spectra for that region and the area that it represents. Okay, so I'm just going to stop sharing this, and I'm going to share this again. Okay, so again, now everyone can see my PowerPoint again.
Yes.
Yes. Okay. So again, I've explained here what to do and different things, different eigenvalues, and go into the cluster analysis and where to look and everything. So I'm just going to go through this real quick, and then I was just giving some examples of if I use the Lukian versus the angle with the same number of clusters again, and the cutoff 0.02 in this case. Just showing these. So this is quick, just the same thing, and again, just telling you about the scaling factor and stuff to look at. So you can see a scaling factor of 0.5 was horrible. It reduced the number of spectra, but it's really cutting into the image of my data. So I've cut off too much data here, and you can see I've only reduced it to there's 5 spectra here, but I'm not seeing what this one here. So you have to play around with the scaling factor. Don't you go too high, you're in trouble. And the cluster analysis, again, you can get here in different spectra. Again, I'm just showing cluster analysis, target spectra. I just showed this, and I take them into axis and overlay, and this is comparing against my linear combination fit that Jan was talking about with some reference spectra. And I think this is actually spectra 2.7. Yeah, so different spectra I'm using here that I collected and done here. And this is all done in Axis. Okay. So next, I want to talk about Mantis, the program. So it's a Python-based program. It's available on net. I hope I've got it here. Oh, I want to actually going through here quick. So this is this is Mantis. It's a non-negative matrix. So sometimes component maps produce cluster analysis using the PCA CA analysis in an axis or standalone. These are slightly negative values which are unphysical and thus represent limitations in analysis. Mantis uses a non-negative matrix analysis to constrain analysis to eliminate these negative values. Okay, and these are references that you can go look. I didn't check to see if they'd published something newer than 2016. But these are talking about Mantis and stuff, and I hope the next slide here will go into this. But these read about talk about how they're doing it and everything, and I'm going to show you in Mantis how to do it again. And then, so I think somewhere I took off. I had it here. Just going through. Okay, sorry. I think I lost the reference for the Mantis, but I can put it on real quick. So I'm just going to leave this now, and we're actually going to go to Mantis now. I think it's just as easy. And again, you have this will be in, I can't get out now. Oh, there it was. Normalizing. Oh, there it is. Sorry. I missed it here. So download Mantis. I see it here. you can just get it at spectrumicroscopy.com and load it on your Windows Linux machine or your Apple machine. Okay, but now I'm just trying to get out of this. End slideshow. Okay. Okay. Well, did you lose me?
We can still see it, just not it's not a presenter view.
Okay. I've lost myself though. Oh, horrible. I don't know how to recover back to. Oh, here we go. Stop sharing. Share. Okay. Okay. I'm back in here. Now I'm just going to go to Mantis now and share and go into Mantis. Where is the Mantis? Oh, yeah, okay. Oh, there it is. Okay. So this is Mantis. It's Python based and it's easy to use. And so the first thing you do is just load your Zane spec stack. And that's what I've done here. You just browse to your thing here and load stack, and you can look at it here. That's just the stack. And again, this isn't an optical density stack. This is just an aligned stack. Again, this needs you to make it into an optical density image, just like the other one. And so you have to go into this pre-processed data and go get the I0 from the file. Okay, so I got the I0 from the file. This is all you go here. There's other things you can do here. You could align your stack in here. The idea of Mantis is the goal is actually to replace Axis, but have a Python version instead of an IDL version. It's not fully operational as the Axis. So there's a lot of things you can do here. You can align stack, limit energy. I'm just going to talk about PC. So now I have an OD stack, and so now I can go do the PCA analysis. So you can save all this. You can play around with this, and actually there's over in Diamond. Actually they've on their sticks and beamline they've actually gone to totally supporting Mantis, not supporting Axis anymore. And so nice thing about Mantis with Python, it's easy to program things if you want it to. If you're into that. With the IDL, it's much harder because you have to buy a license. And last time, long time ago, I knew the license were $1,500 a year, probably more now. And so unless you want to program an IDL, Python's the way to go because it's free. Okay, so now I've made this. I've clicked on this. I'm not going to go find the file. I've already done it. Now I'm into the PCA analysis. So now when it first comes out here, it says that there's only number of similar factors. The default is 1, and it doesn't tell you anything here. I'm going to tell it to calculate. Normally you just tell it to calculate, and now it would show here. And it's doing the same thing here. Principal components showing up to 40. So it's showing the log of the eigenvalues. So this is just the same what we've seen before with the PCA. So she's just incorporated her PCA analysis into here, what they'd done before, and we get the spectra, and we can look at here different spectra. You can go look at up to component 40, I think, or 20. I think you can go to 20. I think she only allows you to see the first 20. Okay, these are eigenvalues. Call them spectrum with their eigenvalue spectra. Okay, and how do you transport those into spectra, I have no clue. If you want to go read up on it, you can find up on it. So I've already told it to calculate, so it has calculated. The cluster analysis. Now again, so if I did this with number of 5 clusters, and I didn't click on this reduce thickness effects, I had the same problem that I saw before when I didn't have enough clusters that I couldn't find this spectrum that I wanted. So that I knew was there. Here, I'm just going to show one spectra at a time that I knew was there. I couldn't find this one if I only used 5 here, and I didn't reduce the thickness. I guess it's something new that she's added here. I haven't found this to be useful. And then you can save these again. It'll put name here. Actually, I'll just show you. We can save here to bring up this extra window. You can save the spectrum as different formats: PDF, PNG. I save them as a CSV file. You can take those into Access as a spectra under multi-column. Here, the images you can save. Probably PNG is what you want if you want to take them into Access. Individual images, PNG again, and scatter plots. Just give it a name, and it'll save it wherever you want. So once you're happy here, you can save all this, and you can go do some other analysis that's not available here. Again, so the scaling factor, I played around with that. I couldn't figure out what it did. I don't know. I think there must be a manual somewhere, but I haven't found it. But I found that the important things were to reduce the thickness and the number of clusters. Increase those.
The scaling factor, basically what it does is it let's say you have the PCA analysis identifies like a second or third component, which in the statistical analysis is not determined to be important, but you as a user have determined that it's important. Then what the scaling factor does is that it sort of increases the statistical significance of lower ranked principal components in calculating the cluster analysis.
I see. What kind of values do you use then? Like, do you remember?
I don't remember exactly what the value is, but the article on Mantis, they give some typical values.
Yeah. Okay. So then again, you can go refer to those references that I gave you. But this is basically just a little bit more than what was in the PCA in Stony Brook. And it's all the same people that are developing it. It's all Chris Jacobson's group that have been developing this. Okay, and then spectral maps, you can go do the same. You can add the same here and stuff, and just do the things there. I didn't do anything here, but I didn't. It's the same. Add your clusters. Go find your spectrum or load spectrum and do things. And here actually you can do RGB. You can overlay the RGBs and you get some nice RGBs. I show that in my PowerPoint. So you can play around with that. So this is more useful than the old PCA because you can now, I don't have to take them into Access. I can do a lot of things here. So what I want to get to here now is we've had to do all this stuff, the PCA, the cluster analysis. We didn't have to do the spectrum maps, but we needed to do those ones before we could take full advantage of this PCA analysis, which we could do before. So now what this allows us to do, we could load in initial cluster spectra. So that's actually what I've done. I've loaded in the 10 spectra here, and I couldn't get this to work until I changed this to 10. I had 10 cluster spectra until I had 5 and it wouldn't work. So you have to make sure that the number of components is matching your at least matching your cluster spectra. And then this takes 10, 15 minutes, so I'm not actually going to do it again to do the analysis. And this is using a number of iterations. You can increase the iterations here. Now this is actually showing 6 spectra. And they are different here. And this is showing the total cost. I'm not familiar with the total cost. I was reading up on it, but I still didn't understand what the total cost was. But you can look at similarity cost, different smoothness costs and stuff. And I haven't played around with these. And again, they're probably in the manifesting the values that you can change here to try and get here. I imagine spectra smoothness depends on how good your data is. If it's if the spectra aren't very good, you probably want to smooth them out more. Here you can load in standard spectra, get it to fit. Initially, I just did random here, and it showed 3 spectra. And it may be hard to see here in my PowerPoint. I take these out. So this is map 1. There is nothing there for map 1. Map 2, it actually found 10, 3, 4, and now we're into 5, 6, 7. I don't know if you can see the contrast here. This is number 7, and actually you probably can't see it. There's actually one for spectrum 6. There is something there. The contrast is hard to see. I missed it initially first time. So how could you give me 6 spectra and only give me 4 images? So then you can go down and get the images, the different areas. And this is actually showing me stuff that I didn't know, that I couldn't find with the PCA analysis. It's going to be, you can't see it here. I'll show it. I can go in the shower PowerPoint. Actually, in this one, there is. I don't know if I can. I don't know how to change the contrast here, but there's actually. It's actually pixels out, and it represents things here that I didn't wear out. The only confusing part to me is that spectra 9. This is 10. 10, I believe, is this red one, and 9 is this one, and it's actually there's an upside down green one here. And it's actually the inverse of here, and I'm not understanding what it's telling me at this time. So it's something that you need to go play around with and figure out for yourself what are the best fittings, and go read the proposals or the papers. I didn't have time. I lost my old computer, like I said, they're afraid of virus, so I took it away from me. So it limited what I could do all week, even, because I was just trying to get things backed up and everything from my old computer. There's other things in here that I haven't explored: Mantis peak ID, X-ray peak fitting. I haven't explored these. These are something. And now she's into tomography here. And I think the latest version is actually she got a beta version that's not available on her website here, but it's version 3, I believe, that she'll be releasing soon. So it's still under development, actually. Is there any questions here? Okay, I'm just going to go back to my PowerPoint. We'll just go here. PowerPoint is here. Okay. From beginning. Okay. So here, I'm just going to click down here to the PCA analysis. Again, you can find it here. It's just telling you how to load, and when it first loads in, it loads in backwards. After you normalize it, it changes to a positive, so you know you've done the normalization. This is just using the PCA GUI, just what I showed. Again, and you can go look at different ones. Mantis cluster analysis. Again, the same. And you're still getting the same problems that you had in the one in Axis. Here, and I also noticed that you could get different results when doing the calculation second time. So there's some variability that when I do the calculation again and again, it changes it a little bit. You can save these cluster, and then you can save all these things, and again, you can save them. There are spectral maps. You can go in and do the spectral maps and find things. You can overlay. You can bring up this RGB that I didn't show, and overlay the different spectra and change the components, the weights and stuff. And you can make composite maps that, again, that you can do and play around and save it. And again, this is where for the Mantis program itself here and the non-negative matrix analysis, there's two papers here. I don't know. I think they should have had another one out in the last 4 years. I didn't have a chance to go look. And again, this is just what I was showing here. Excuse me. Okay, and then just showing. This is why you can see 5 and 6. I hope you can see them now. That there is something here. 5 and 6. These are the same spectra that were here. You can see that this is different than here, and this is actually a little bit different here. So, but I'm confused why this one's to me it's upside down. If when I multiply it by -1, it's the same as 10. But it's showing different area. Okay. Next is correlation analysis. We're just going to go into this. This is just using image J. This is actually with some other data, but no. So now we can look at our RGBs and we can get some see color images and see where they're overlaid. But it's always nice to get some math, and so you can go use correlation analysis, and the ones that's preferred is this Pearson's coefficient or Mandarin's, because it takes into account intensity. So Pearson, you can go look up this paper here. It explains the difference between Pearson's and Mandarin's and tells you why you want to use Pearson's and not Mandarin's coefficient. Okay, and so I use image J. There's different ones. This is the original one from the National Institute of Health in the U.S. government. But image J, there's lots of different packages. I find the Fuji package is a good one to go to. You get Fuji. This is an older one that I used to use. The Fuji one is nice, and you can put in plugins. There's different plugins that you can do. There's lots. If you go to this site here, you can find a lot of plugins that may not be in here, but a lot of them are in. So you can add more plugins, and that's the next thing I'm going to talk about is that there's a plugin by Martin Oops. This is grad student here, Martin Oops. They made a scatter J. Allows you to do some backscattering here. You can go in and read the paper. You go and get the plugins from here. And it allows you to do some nice things. You can go in and take different areas of your image here. Like here, they're taking 2 different images and get the spectra from the 2 different images. And you can actually see where it is on the image and stuff. It's something really nice to go use, and it's it's an image J, a plugin, and you can use both. You can go to the paper and get the information. And this is just how to put plugins in, file, name. You can put plugins in here. I don't want to. And then image scatter J comes up. You can create a scatter plot from images that you load. I don't know if you're familiar with loading images. Normally they're TIFF images. If you're going to load a TIFF image from Axis, you want to make sure that you remove the scale bar, because the scale bar will become part of the data. So before you save it, you want to make sure you remove the scale bar in Axis. And I save them as TIFF data files. And you can see here different areas here. You can't see that because I haven't shown it here. Different things here. This is just overlapping, and you can get your Pearson's coefficient here, and it shows where they are correlated and stuff. And you can go in and take areas, like I said. So this area here, you take this here. This is for here. gives me a different individual Pearson's coefficient here. If I just go circle here, this is the pixels. These pixels are from this area, and you get your coefficient. And you can change all kinds of things in here. But the real numbers at the start, it's not putting the real numbers. It's using the 256 scale of image J. But you can go in and put in real numbers and do here. This is just in the color scale axis, and then you can export the data. You can get more different statistics here. And that is the end of my slideshow. Is there any questions? End of my talk, really, too. If there's any questions, all this I'm going to put on the website somewhere, and also the data that I used for the PCA analysis. Are there any questions? I explained everything perfectly. That's amazing. Both Jen and I are amazing. Explained everything perfectly. Okay, I'm going to stop sharing. Any questions from anybody? And if you're not on our list, just email Jen, Ying, or myself, and we'll get something out here. I think we'll get Ying to send something out where all the data is and everything, and the PowerPoints. And we did record this, and so there will be a recording too, which I think will be available on our website. We did this a year and a half ago, and we actually recorded it. So there's some new stuff in here that wasn't in the old recording. So if you really want to sit through the old recording too, you can sit through that one too. Jan, do you have anything you want to say, or?
I think it's great. So I just wondering, what is the best way to share the files and the information? Is the WebEx providing some online storage for share, or we have to use CS, FTP, or what other network drive like Google Drive or something?
Yeah, I think we'll just put it on our webpage. My extent there for forever. It's hard to put? Okay, we'll figure it out. Ying will tell us the best way.
Yeah, I used to use FTP, like a user can download their data. I just create a folder there and throw the file there, and they can download. Okay,
so FTP. Okay. So it's just the same as you'd go into get your data, the FTP.
Yes.
But we'll have to tell you where it is to make it easier for you to find it. Okay, so this week I'll get it in there and stuff.
Yeah.
Is there anything anyone wants to ask?
Yeah, I think any questions regarding STXM experiments, data analysis, even scheduling? Yeah.
Or when users might be coming back? Is anyone interested in that? So right now, I think U of S users, some might be coming back in January, University of Saskatchewan. And actually, anyone from Saskatchewan, I think we're calling on anyone from Saskatchewan is going to be allowed to come. Anyone from outside isn't going to be allowed to come right now. I think that's right, Jan?
Yeah. So the only local users are allowed to come on-site, one person each group in the next round, which is from January to March, the first half of that next round. The second half of next round, May to June, will be evaluated, I think, next year by the management to see if user will be allowed on site fully for international and national users. Right now, from the next January to March, only Saskatchewan user will be allowed one person from each group on site for experiment.
And so I say international or outside Saskatchewan users, maybe might see something. Might have to produce a COVID vaccine certificate or something. I don't know what's going to happen.
Yeah. Yeah, for the remote operation of STXM, from July to September, we run STXM remote operation for all the users, which worked very well. The software we are using were VNC, VPN plus VNC, it works properly. So hopefully we can get other software like right now that's no machine looks like has some challenges to work. Maybe we can try either like AnyDesk or other software for remote operation.
Yeah, but I think our users were happy that they didn't have much trouble.
Yeah, we also can do mail-in services. Like you send a sample to us and make a very detailed measurement. At least the Beamline staff can measure for users.
So I have maybe a few. We still have time, but my questions and kind of comments are. I don't know, maybe a little bit niche or maybe more advanced. I don't think that anybody else would benefit from them. I've been doing some, basically creating artificial stacks in STXM. So using standards to create a stack, like a pseudo particle with heterogeneity, and then doing like principal component analysis and non-negative matrix analysis, and looking at the results and then kind of comparing them to the input data, and I've learned quite a bit, but admittedly I'm still not nearly as experienced as you all, so I would be open to some feedback. But for example, I don't know if it's ever been explicitly stated as to like what the principal components, what the spectra of their principal components, what their physical meaning is, for example, and how they're determined and all that. Do you guys have any intuition for how like in Mantis, for example, when you do the PCA, you get spectra, but it's not, it's the spectra of the principal component and not necessarily the clusters?
Right. I think you have to go read her earlier papers by Jacobson on how the eigenvalues and eigen stuff is being switched, the math into switching it over to spectra.
Okay.
If you read those earlier papers by Jacobson.
The other kind of question that I have is, what I noticed is that sometimes when you have a particle, even if it's fairly homogeneous in thickness, when you're doing the SVD or the spectral maps, how can you deconvolute? Because there's, if you look at the matrix, there's a contribution. It's basically a thickness map and also a spectral weighting map, and that determines the intensity of the SVD map. But sometimes we're interested in just the spectral weighting and not the thickness component of it. How do you guys have a way of dealing with that?
Yeah, maybe I can comment. That actually is the exact difference between the stack fit and the SVD. For SVD, all the optical density value will be distributed into the components. For the stack fit, you will see optic density distributed partially to the components, and also there will be constant. The constant is the OD constant, which probably is the thickness effect problem.
Okay, so to reduce the thickness effects, stack fit is better than SVD?
Yeah, I think so. Yeah.
Okay.
Or what I do in SVD is I actually put in a constant value. I put in a low sloping value line and use that as my constant. And that'll map out some thickness stuff.
Okay, and the SVD maps.
Yeah, so you add an extra spectra. You have your reference spectra, but then you also do that. I think we've explained that in a couple of our papers. If you email me that, I can email you some of the paper. I think our earlier ones with Adam, we explained using a low sloping spectra. I know I always do it, and Adam I think does it, and Martin Oops does it, and so.
Okay. The other, I guess, thing that I've noticed sometimes is just due to the inherent way that STXM works, where you're scanning, basically what I see sometimes in the analysis, the outermost layer of the particle gets grouped in with background. And so your background spectra looks like your sample spectra, but at very, very low optical densities. In other words, it's just like it's getting the very edge of the particle, because basically what happens is that at the boundary you have a pixel that is describing both particle and background. Do you have like a recommendation for how to eliminate that?
Yeah, well in Stack Analyze, you can go in there and you can pick the intensities that you want. Do you use Stack Analyze to align your stacks?
Yes.
So then you get a histogram there. You can go pick which you want, so you can select the higher amount. Also, you have to be cautious is that most of our samples we put on there with water, right, onto a grid and stuff. So some of that actually may be real. In the I0, that you've had some dissolution of your material. So if you're using water or some solvent, you have to be aware that some of that could be real, and we ratio it out. So we still have the I0, but you may be losing some of your quantitative information.
Okay.
Well, if that's it, I guess we're going to leave and go have lunch.
Okay. Yeah. If anybody doesn't have any questions, maybe we can stop for now. And if you have questions in the future, just feel free to email me, my staff. And
we're quite happy to help you other times, and even if you need one-on-one on a Skype or Zoom meeting or something, we're happy to help you that way too. So if you need more help understanding things and can't get things working, we're prepared to help you.
Yeah, that's right.
Okay, well, thanks everyone for coming.
Yeah, thank you for your participation.
Thank you.
Thank you very much for participation.
Okay.